Welcome to the Math 123 Rollcast. We're Group 38, and the group members are Bob, Yolanda, and Iris. In this video, we're going to present the basic theory of derivative and using actual problem to talk about how derivative used in real life. The concept of derivative is at the core of calculus and modern mathematics. The definition of the derivative can be approached into two different ways. One is geometrical, as the slope of a curve, and the other one is physical, as the rate of change. Historically, there was, and maybe still is, a fight between mathematicians, which of the two illustrate in the concept of the derivative best and which one is more useful. We will not dwell on this. Our emphasis will be on the use of the derivative as a tool. Let me give you a quick introduction of the history of derivative. Before Newton and Leibniz, the word calculus was a general term used to refer to anybody of mathematics. But in the following years, calculus becomes a popular term of field of mathematics based upon their insights. The purpose of this section is to examine Newton and Leibniz's investigation into developing fields of infinitesimal calculus. So what is derivative? It is the rate of change of one quantity in terms of other quantity. So for example, if you want to know how something changes in times, you usually need to invoke a derivative. This could be something like the position of an object, of the strength of an electric field, or quantity of water in a container, or the amount of money in your bank account. It is to say that it would be essentially impossible to do any physics without derivative, which would mean no modern engineering, which would mean essentially no technology developed after the 70s.
Hi, I'm Yolanda. I'm going to give an example of how we use derivative in our real life. For example, we want to make a cube with no cover using a piece of square iron sheet, which the length is 60 centimeters. First of all, we cut 4 small squares in same size from 4 corners. Then, we fold it following the dashed line. So, the question is, what the length of the cube should be to maximize the volume, and what is the largest volume? Assume that the height is x and the length to be 60 minus 2x. Then we will have an equation of volume Vx equals to x times 60 minus 2x squared, and the range for the x is x larger than 0 and smaller than 30. Then we'll spread the equation, and the next step we need to find the derivative of Vx. And the next step is at stationary point, derivative of equation Vx is equal to 0. That means 12x squared minus 480x plus 3060 is equal to 0. To solve this equation, we need to find delta, which is b squared minus 4ac, and it is equal to 400. Because it is a positive number, that means we have two roots for solutions. Then we can calculate x using x equals to minus b plus or minus square root delta and divided by 2a. So then we will have two solutions, which one is x equal to 30 and the other one is x equal to 10. Because x is less than 30, and when x is close to 0 or 30, the volume would be too small, so the answer can't be 30. That means x is equals to 10. Then we substitute 10 into the equation Vx. We will get the answer of the volume, which that means the largest volume is 16,000 centimeters
Hello, I'm
square.
Maris. Today I will show you an example of the practical application in the derivatives. A local government wants to start science and technology activities, so it wants to map an irregular non-agricultural land into an industry park. As it's shown in the picture, AB is perpendicular to BC and OA is parallel to BC. OAB equals to BC equals to 4, and OA is as half as AB, so OA equals to 2. OC is a parabolic, which y equals to root x, and P is a moving point on the OC, and its coordinate is x, root x. So we could get that PQ equals to 2 plus root x, and Pn equals to 4 minus x. Here is the PQ equals to 2, and here is the root x, and Pn, here is the Pn equals to 4 minus x. Here's the x. The government wants to find the largest industry park area, which equal to PQBN. So how could we get the largest area here? First, the area equals to PQ multiply PN, which equals to 2 plus root x multiply 4 minus x. When the derivation of s equals to 0, we could get the x equal to 4 divided by 9, and here is the x when we could find the largest area, and take the x equal to 4 divided by 9 into the area here, which equal to PQ multiply PN. So we could get that the max of the area equal to 259 divided by 27.